You know, we've all done it. You get a headache, you pop a pill. Your allergies are acting up, you take a little tablet. But have you ever really stopped and thought about it? How in the world does that tiny thing know what to do? Today, we're going to pull back the curtain on that microscopic magic.
I mean, it really does seem like magic, right? How does an aspirin navigate the labyrinth of your body to find your headache? It's not magic, not at all. It's actually a brilliant and incredibly elegant system of communication.
Okay, so I want you to imagine something. Picture your body as this huge, sprawling, bustling city. And inside this city, there are trillions of residents, your cells. For the city to work, for you to think, to move, to even have a heartbeat, all these cells have to be constantly talking to each other. And it's this communication network that modern medicine has learned to tap into.
Right. So, if our body is this city of communicating cells, how exactly do they talk? Well, it turns out every building, every single cell, has these super specialized locks on its surface.
Now, these aren't your typical metal locks. They're actually these intricate protein structures, and their scientific name is super important, receptors. And you gotta remember, each one is incredibly specific, shaped just right to accept only one kind of chemical key. When that perfect key finds its perfect lock, a message gets delivered, and the cell springs into action. And what's really cool is that not all these locks are built the same. You've got your simple doorbells. Scientifically, we call them ligand-gated ion channels. A key hits this, and bam, a channel just swings open. It's super fast, super direct. But then you have the smart locks, or GPCRs. That's short for G-protein-coupled receptors. And these are way more sophisticated. When a key binds to one of these, it doesn't just open a door, it sets off a whole chain reaction inside the cell.
And hey, if you're wondering just how big a deal these smart locks are, get this. Over a third, 36%, of all drugs approved by the FDA are designed to target these GPCRs. Why? Because they're involved in pretty much everything. Our sight, our mood, our heart rate, you name it. They are one of the most important targets in all of medicine, period.
Okay, so we've got the locks on our cells down. But what about the keys? This is where the real genius of drug design comes in. We're diving into the world of pharmacodynamics. And don't worry, that's just a fancy term for how drugs actually work on the body. See, your body already makes its own keys, things like hormones and neurotransmitters. The sciencey name for these is ligands. What drugs do essentially is act like man-made master keys, engineered by scientists to fit into those very same locks to either copy, boost, or even block the body's own natural messages. So let's just nail down this term, pharmacodynamics. It's really simple when you think about it. It's the study of what the key, the drug, does to the lock, the receptor. That's it. It's all about that one critical interaction.
Okay, and this is where it gets really cool. Because not all keys are made to just open the lock. Scientists can actually design these keys to do a whole bunch of different things to get exactly the effect they want.
First up, you've got the agonist. This is your perfect key, a perfect copy of the body's natural one. It slides in, turns the lock all the way, and boom, you get the full maximum response from the cell.
Then things get a little more subtle. You have the partial agonist. Think of this like a key that wasn't cut quite right. Yeah, it fits in the lock, but it only turns it part way. So you get a response for sure, but it's way weaker. It's like turning the volume down to a 3 instead of cranking it up to 10.
Now this next one is just a brilliant strategy. It's the antagonist. Imagine a key designed to snap off right in the lock. It fits perfectly, slides right in, but it does absolutely nothing. It just sits there, completely jamming the keyhole so no other key, natural or not, can get in. It's a total blocker.
And for our last one, we've got maybe the cleverest of them all, the inverse agonist. So picture a lock that's kind of faulty. It's always a little bit on, even when no key is in it. Like a leaky faucet, right? An inverse agonist, it actually grabs that leaky lock and forces it completely shut, actively quieting down that background noise.
So let's just recap that because it's so important. We can make keys that turn the signal all the way up, keys that turn it up just a little, keys that completely block the lock, and even keys that force a leaky lock shut. This amazing toolkit is what gives medicine its incredible precision.
Okay, so that's the theory, but how does this all play out in the real world with actual medicines? Well, understanding this whole lock and key thing isn't just for textbooks, it is the absolute foundation for how we treat so many diseases. I mean, just think about it. Anesthetics. A lot of them work by hitting those super fast doorbell receptors to shut down pain signals instantly. The Alzheimer's drug memantine, that's a classic antagonist. a blocker key for a specific receptor in the brain. And modern antidepressants? So many of them are designed to be these fine-tuning keys for our serotonin system.
And that really gets to the heart of where medicine is heading. As we map out more and more of these locks in the body, the game is changing. It's less about stumbling upon new drugs and more about intelligently designing smarter, better keys for the locks we've already found.
So, every time we find a new receptor, every time we design a new molecular key, we're taking one more step towards a future of incredibly precise, personalized medicine. It really makes you wonder, doesn't it? What disease will we design the perfect key for next?